All right, it's 40 after, so we'll go ahead and get started. I'm going to continue today with thermodynamics, and I'm really going to focus on PV diagrams for an ideal gas. That's going to be our main thermodynamic system. It's going to show up for sure on the final. You definitely want to know how to use PV diagrams. Think about them. And in particular, there's only a couple equations you need for this part of the class, really. And that's true for every part of the class. There's only 2 equations, right? This class is not that, there's not that many things you need to know. It's just you need to know how to apply them in a huge number of different situations, right? Just a few equations. So before I get too far into this, make sure I got any business. Oh yeah, practice finals up on the B-space. I'll put up some solutions to those pretty soon. Treat them like an exam. Time yourself. Make your formula sheet first. You can use both sides. Same rules as the second midterm. But go ahead and make a new formula sheet so you really get all the new material. The final's going to be focused, not entirely, but largely on the new stuff. So make sure you get everything on there. And then we can test out your cheat sheet and see if it's giving you what you need. And you can be honest with yourself about what you're getting and what you're not getting about the course. Oh yeah, teaching evaluations. I'll pass those out at the end of next class. So the last 10 minutes of Tuesday's lecture, I'll pass out, or I'll have a volunteer pass out teaching evaluations. I'll stand here while you're filling them out. I'll be out of the room. And then I'll have office hours as usual in the back afterward. Okay, good. So there's only 2 chapters from the book. We're in chapter 18 today. A little bit of chapter 19 today, depending how far we get. And then next time we'll continue on with chapter 19. So PV diagrams. All right. Let's see. Let's start. Oh yeah. So what are our equations? Well, we have the first law of thermodynamics, right? Which is just conservation of energy. That's all it is, right? It just says the change in the energy of a system. You can use U or E. I like E because it reminds me that it's all kinds of energy is equal to. And again, I use my notation here. Q for heat, and I write in. This is the. So if Q in is positive, heat is being added to the system. If you add heat to the system, the energy goes up for that system. Just like for all problems in this class, you want to keep straight about what system you're talking about. It's not the ideal gas. We really mean the gas inside the cylinder. That's the gas we're talking about. That's the system. But we can also talk about the energy of the thing that's providing the heat bath. We're going to do that too. So whenever you're doing this, make sure you know what the system is. And then of course there's another way to add. How else can I add energy to a system? What else can I do? I can do work on it. And to get my sign right, I have a plus sign here. I better be work on or work by. Better be work on. Correct. The book uses the other definition. It doesn't give a subscript. But when they write W with nothing on it, they mean work by. I just write either on or by, just so it's clear in my mind what I'm talking about. So good. Everybody's positive. Add heat or you do work on the system. The energy changes. It's really important to distinguish between these different kinds of energy transfer. We'll see how far we get today. But by the end of class, I'm hoping to have introduced the notion of entropy. You've seen that in other contexts. In your chemistry class, you've seen enthalpy and other things like that, which are related. Energy and entropy. These are both state variables. And I'll talk about what I mean by that. It means if you know where you are on the PV diagram for an ideal gas, you can right away say, you know for a fact that there's a well-defined energy and a well-defined entropy for that state. They're state variables. These things are not state variables. The amount of work I did on the system, the amount of heat I added to it, that can be different leading up to any given state. I could have gotten there any number of different ways. I could have added some heat or done some work, some combination. So these things are not state variables. You can't tell what Q or W is based on where you are on a PV diagram, right? And like I was just saying, it's important to distinguish between these kinds of energy transfer because transferring heat, if you transfer heat from one place to another, entropy, at least locally, is changing. And I'll talk more about that later in the lecture, and we'll talk about a lot too in the next lecture. But when you do work on a system, work is special, right? Like even earlier in the class, we often talked about potential energy as being potentially able to provide useful work. When you do work on a system, you don't actually change its entropy, and you don't and no entropy is changed. Let's see how I say this. Let's just leave it at that for now. You do work on a system, you're not changing its entropy. It's only exchanges of heat that matter. So I'm just saying a bunch of stuff in words that we'll get into as we go. I just want to have these things in your mind as we go. So this is a general law for all thermodynamic systems, but we have specific rules for a monotonic ideal gas. Let's see, monotonic. I think that's right. I think it's mono or mono. I'm not even sure. But all it needs is this is just an ideal gas that is composed of single atoms. The molecules only have one atom apiece. So in that case, we get 2 new rules. In fact, you can combine them and get a third one that's kind of convenient, even though, just remember, it's not going to be independent of the first 2. One is that, as we worked out last time, the energy, instead of an ideal gas, it just equals 3/2 times NKT. And as you know, this 3/2 that depends on assumptions about the details of the structure of the individual molecules. If you have a diatomic gas, it's 5/2. But we'll just stick with 3/2 today. And I think I'm not going to test you on the final on different factors in front. You'll be able to count on it being a monotonic ideal gas. You'll have homework problems that depend on that. And the book describes everything more generally, but I'm going to stick with this. Just because I think you're doing great if you can figure out what these things do for monatomic gases. That's a lot to learn in the next week and a half, so we'll stick with that. PV equals NKT. Everybody knows this. If we combine these things, NKT appears on both sides of each of these equations. So we can combine these and get another expression for energy as a function of PV. It's that energy for a monatomic ideal gas equals 3/2 times PV. That's useful, right? So we have these relations that are special for gases, for ideal gases in particular, right? And then a general first law of thermodynamics. Okay, great. So we can use those things to figure out what's going on in a variety of situations. I already walked through real quick right now what happens with the constant pressure, and then we'll go through a bunch of other types of transitions you can have on the PV diagram and see what the energy looks like, see what the temperature looks like, see what Q and W, what they are equal to. It's important to be able to calculate all this stuff. This is going to show up later. So here we go. PV diagrams. Now, whenever I draw a PV diagram, what I always mean by it, unless stated otherwise, is we're talking about some kind of ideal gas. In this class, it actually will always be monatomic even. And not only that, but this is a representation of a bunch of states of the system. In other words, if I choose some point on this graph, there's a well-defined pressure and volume, and there's also a well-defined temperature. Okay? I'm also assuming that the number of particles is fixed. So that's also well-defined. I'm not going to ever write it out on my diagram what n equals, but the problem description would have to tell you. You'll be able to figure it out from something else. But n is fixed when you have diagrams like this. Temperature is not fixed. As we figured out last time, temperature varies throughout this plot, and it varies according to this equation, right? The bigger P times V is the bigger the temperature. So high temperature, low temperature. Great. So let's just do this one more time. We've got some point here, and you say, all right, what if we take a system that starts off at this value for P and V, and now we move it over here? So let's expand the gas. I say expand because the volume got bigger. So if there's an expansion, I can then calculate all these things I might want to know. How much energy change was there in the system, my ideal gas? What was the change in how much heat was exchanged? What was the work done? We know how to do work. That's the one we can use it easiest to calculate just going through the math, right? So the definition of work, we say, okay, we've got work on. Work on, remember, is negative integral from V1 to V2 of P dV. Well, the integral's not too bad here because P is a constant, right? P doesn't change throughout the entire motion here. So what do we get? We get, it's just P1 times delta V, where delta V means V2 minus V1. So delta V, is delta V positive or negative in this case? Going from left to right. It's positive. V2 minus V1 is a positive number. So then work on, I claim then is negative because pressure, this is absolute pressure, right? So that means it's always a positive number. It can be 0, I guess, but it's never negative. So this is positive, not positive. The whole thing is negative. Work on is negative. Does that make sense? Yeah, because the gas expanded. So in other words, the gas did work pushing outward, right, as it was the whole time, as the plunger in the piston moved outward. So the force of the gas, due to its pressure, was in the same direction as the motion of the plunger. The gas did positive work on the outside world. So W by was positive. That means W on is negative. All right. So now what about the rest of it? Well, if I want to figure out what Q is, what the heat exchange was during this process, I say, well, I know what the energy change was, delta E. And I can once I know what delta E is, I can just plug these things in up here and figure out Q in is. What's delta E? Oh, I'll just figure out what the change is from here to here using this expression. E is 3 halves PV, right? So that P is the same in both cases, so that means it's 3 halves P times delta V. Everybody agree with that? I'll put P1 to indicate that I mean. So normally I'll indicate it like this. I'll say here's point 1, here's point 2. In this case, the pressure didn't change, so P2 equals P1. And I'm just choosing to call it P1, but as long as it's there, which one I mean, that's fine. So P1 times delta V. So did the energy go up or down? Positive, positive, positive. Energy went up. When you go that way, energy goes up. We talked about this last time. We said, oh yeah, the work on was negative. The energy increased. If you do negative work on the system, which on its own would have lowered the energy, but the energy itself went up, then did you have to add heat or take heat out? So with these equations, is delta E positive or negative for this process? Come on, give me some. Positive, I agree. Is work on positive or negative in this process? Negative. So what must Q in be? Got to be positive. It's got to be bigger, in fact, than work on, right? Good. All right, just make sure you guys are. I'm just forcing you to speak up. It's okay. All right, so what is all that? It's delta E minus work on. If I got my signs right, I think I do. I just took the first law and reverted it around and see, okay, then what does that equal? Oh, it equals, well, let's see. It's minus this is a positive number, right? So I get 3 halves P1 delta V minus a negative number is plus P1 delta V. That's a pretty simple formula, right? 3 halves plus 1 turns into, let's see, it's 2 halves, it's 5 halves, right? It's positive 5 halves. As advertised, it's bigger than 1, right? It's bigger than just P1 times delta V. P1 delta V. So great, we just calculated all 3 of the things I might want to know. I guess you might also know some other things too, but those are 3 things you might want to know. Delta E, Q, and W. How do we do it? We directly calculate the work. We directly calculate the change. I mean, we actually, so let me make it really clear what I did here. I combined these equations right off the bat to get a relationship between energy and P and B. I could have also done it with an intermediate step, where I say, well, what's the temperature? Right? In fact, I could calculate what the temperature is explicitly by just plugging in, and here's the answer, right? Temperature is P1 times V1 over NK. Well, if I'm not given NK, then I have to leave it in symbolic form. But notice I was able to figure out I was able to express everything. Oh my goodness. I was able to express everything in terms of, let's see, do I know what N is? Can I figure out what N is? If I know what, if I know, let's see, it depends on how much these things I'm given. But anyway, the bottom line is this. We can calculate all these things. I did 3 of them. I can do the last one, temperature, just by rewriting this expression, PV over NK. So good. I can do all these quantities. The only one I did with an actual calculation from first principles really was the work, I guess, in the energy. But the heat, I didn't separately figure out the heat. I just used the first law. That's normally what happens. It usually turns out to be easier to calculate work than the heat. But there are some cases you get given some problems where you know what the heat change was. You figure it out from from part B or D, or you're told, and then a later part of the problem, you're asked about the work, and you won't directly calculate. You'll use the first law, right? So, okay, very good. So what's the next thing to consider? Next one to consider is where it goes from here to here. All right, so we got our PV diagram. Let's see that it's going down. So this is neither a compression nor an expansion, right? Because V is not changing. But the pressure's changing. You have P1 up here and then P2 down here. So I label this as point 1 and this is point 2. And then we'll just say, oh, V1, same thing as V2. We'll just call it V1. So in this case, so right off the bat, what's the work? And this, we did this one last time as well. What's the work here? I agree. Work on is 0. And the simple way to see that is the area under the curve is 0. If you look at this and say, oh yeah, the work is calculated just that rectangular shape. Because it's a really simple integral. It's just a constant times the difference, right? Great. So work is 0. We're already a third of the way through figuring these things out. You say, okay, then what is the heat exchange? So to figure that out, again, let's follow the same process. Let's look at the difference in the temperature, in the energies. What's the energy change? Say, oh, it's, let's see, it's 3 halves PV for an ideal amount of gas. So that means that it's, let's see, what's changing? Well, in this case, what's changing, V is the same, right? But P has changed. So I've got P2, V2 minus P1, P1, oh yeah, but V2 is equal to V1. So this just becomes 3 halves delta P times V1. Does everyone agree with that? Pretty simple. If that's the change in the energy, then we're done, right? We know what the change in the heat has to be. Oh, let's make sure we have the energy in the right direction. Did I get the sign right? So is delta P positive or negative in this process that goes from high to low? It's negative. The final pressure is lower than the initial pressure. So P2 minus P1 is a negative number. Is that right? P2 minus P, yeah, it's a negative number. And that means that delta E is negative, and that's correct. If you go lower in the plot, go straight down, we're going to lower temperatures. Lower temperatures are lower energies, right? And we can explicitly calculate the temperature, right? So yeah, go over there. Temperature is just PV over NK, or if you like, it's 2/3 E over NK. So we can calculate the temperature explicitly from the energy. When I just write down just to be pedantic. Okay, what is that? It's equal to, let's see. There's several ways I can write it. It's 2. I'm going to write out longhand. It's going to cancel. I'm just using people's NKT. So I get 2/3. Oh no, let's do it this way. 2/3 times NK in the bottom, and I've got a delta E on top. I think that's legal. I got my 3 in the right spot. 3 in, yeah, looks good. And then I say, all right, I've already calculated delta T. It's 3 halves. That cancels with that. So we get delta P over V1 over NK. Okay, just to be pedantic. So yes, we do need to know N if we're going to go a step further and say what the temperature is. In other words, suppose you have a certain amount of energy in the gas, but you don't know how many particles there are inside. How many atoms flying around in your gas? You can have the same energy by increasing the temperature, increasing the average kinetic energy of individual molecules, and just having fewer of them, right? And for an ideal gas, you can't tell the difference. If all you know is the pressure and the volume, that isn't enough to tell the difference. In principle, you just have one particle that's banging around so hard that it's as if you got a room full of cooler particles. So that's why we still need to know this to get the temperature out. But if all you know is the change in energy, you don't need to know how many particles there are. All you need to know is what P and V are initially and finally, right? And what path was taken. Actually, is that true? No, for delta E, that's not true. Any path I take from here to here results in the same change in the energy. After all, when we calculated that, we didn't do any integral over the path or something. What we did was we just said, what's the energy here? What's the energy there? Energy is a state variable. I can calculate it for any given point in this diagram, no matter what path was taken to get from A to B. Whereas the work, that's not true for the work. The work is equal to 0, and that went from here to here, because of the specific path that was taken. If I took a different path, there could have been positive work or negative work done, right? That's really important. so work is not a state variable. That's what I mean when I say it's not a state variable. Same thing with the heat. The amount of heat I had to exchange with the gas is not a state variable. Taking different paths between 1 and 2 results in different amounts of heat exchange. Now there's a relationship between work and heat. If you give a little more heat, in this case, the work done was 0, but the heat exchange was non-zero. We can calculate explicitly from the first law, right? We say, oh, what's Q in? It's equal to delta E minus work on. Same old. What is delta E? It's right here. It's 3 has delta P V1. What was work on here? Oh, 0. So there's our answer for how much heat we had to exchange. But suppose instead of going straight down, I took a different path. Suppose I went out this way to a very low volume, and then went straight down and came back that way. That would result in non-zero work. Because going that way, there'd be area under the curve, come down, go back this way, there'd be a different area under the curve with the opposite sign, but they wouldn't cancel out. One would be smaller than the other. That's what an engine does, and we'll get to that in a few minutes, but I just want to make it clear what we're doing as we go here. So the fact that it went straight down, we needed that fact to calculate how much work was done on the system. The change in energy from that point to that point, doesn't matter what path it is, we calculate explicitly, we know exactly. Same thing for temperature. The temperature difference between point 1 and point 2, temperature is a state variable. That change in temperature doesn't matter how you got from A to B, or from 1 to 2 in this case. All that matters is what the final initial states were. Okay, great. I know I'm just beating this about the head and shoulders, but it's worth repeating. I guarantee many of you will you'll be glad you know it in the final. Okay, great. So good. So I think we've got this. What else do I want to do with this? I think that's all the stuff I want to calculate for this case. So these are the easiest cases because they're straight paths. They're either horizontal or vertical. There are some very important cases, though, that are a little bit complicated. So let's go over those. There's 3 complicated cases that are really important. One of them is isothermal, or constant temperature process. So we've done constant pressure, constant volume. So what does the constant temperature look like? Constant temperature looks like this. How much is enough for it to see it? This will probably be okay. We can get our PV diagram. Well, we know that there's high temperatures up here and low temperatures down there. If you start off at the same point you started here, some P1, V1, right? V1, and I want to move along a constant temperature curve. What does that look like? Well, PV equals NKT tells me the answer to that. If I fix T, then I have PV equals N, which is a constant for our assumption here for PV diagrams, and K is constant, T is constant. So PV is a constant. PV is a constant means that P equals V over NKT. Did I get that right? PV equals NKT. No, I don't like that. PV equals NKT. Oh, no, I did it all upside down. NKT goes on top, V goes on the bottom. That looks a lot better, doesn't it? Yeah, I like that. So P goes like 1 over V. What does that look like? It looks like this. Right? So for any given temperature, you've got some constant temperature curve like this. Just an inverse, 1 over sort of relationship. So if you start right here and you go at a constant temperature and you let the gas expand, all right, to some new volume, you go here, it follows a curving trajectory. So it's not exactly a straight line. As I drew it, it looks kind of straight because I happen to choose one that didn't have too much of a curve to it. But if I go closer to the origin, it gets curvier. But you get the idea. I'll exaggerate the curve a little bit. It's curving. So let's figure out what to do with this. If you have a curving trajectory like that, well, now when you calculate work, we have to worry about the facts that you have an integral, right? So here's our V2. Here's our final V. Does everyone see this okay? V1, V2, P1. Now we have 2 different P's and 2 different V's. Oh, sorry. 2 different P's. We've got a P1, P2, V1, V2. Area under the curve is the work, just like always. We're going to the right. So is work on going to be positive or negative if I'm going from left to right in the diagram? Work on. So the gas is expanding. It's pushing out. The work it's doing is positive. So is work on going to be negative or positive? Negative. Just like it was over here. Exactly the same. So in this case, for constant pressure, we went from left to right. It was a horizontal line. It turns out that no matter what path you follow, it doesn't matter if it's curving or straight, if it's going up or down, whatever. If it goes mostly to the right, and it doesn't, well, if it goes to the right, it doesn't double back on itself and get complicated. If it's going to the right, then you know that the work by the gas is positive, the work on the gas is negative, and vice versa if you go to the left. So yes, this is negative work on. And if we're going to calculate it, we have our formula. It goes negative from V1 to V2 times, what is it? P times V, right? Oh, P times dV, excuse me. We're doing the integral, right? What is P? Well, I've got the formula for it right here. It's got a bunch of constants on the top because we're going constant temperature. T is a constant. K is obviously just Boltzmann's constant. N is fixed for PV diagram. We've got gas, no particles are leaving or entering. So this is all a constant. But it's got a dependency like 1 over V. So what's that look like? Well, I'm just going to pull out the NKT in the front. There's always NKT floating around with this stuff. We're integrating from V1 to V2, right? And now we've got dV over V. So what is the integral of dV over V? Yeah, that's right. So if it were any other power, if there's any power than -1, you do that thing where it's like this is v to -1, right? You say, oh yeah, it's -1 minus. You add 1 and then you put the. Anyway, but this power results in a logarithm. It's the only power that gets kind of weird. It's all right. So logarithm, you guys all know that. You can forget it because you never read it again, right? Now you have the formula and you use it on. You can use this out of the box. But I'll go ahead and work it out just so we see where it comes from. So we've got NKT. Actually, the book goes pretty haywire with all kinds of this stuff. It gets into specific heats of gases. I'm not going to test down specific heats of gases. Might show up on a homework problem. But the math is a little bit. There's a bunch of funny integrals and funny things that come up with that stuff. Not even integrals, but just dealing with a lot of complexities that I think take us beyond the basic things I want you to learn. So, but anyway, but do each section and do all the homework on the exam. This is the kind of stuff you can expect. You're not going to actually solve the integrals per se, but you should know this formula. You should know the result of this one. So we have NKT dV over V. Oh yeah, it's a log of V. Well, if you have a log of V and you're valuing it V2 and V1, there's a minus sign in the front. So if I leave that there and just evaluate this, well, the log V1 minus log V2 minus log V1 is equal to log of the ratio V2 over V1. Does anyone not believe me? Does that look right? Got a minus sign in front. I could get rid of the minus sign and flip those if I want. That's okay. Just be familiar with how to use a logarithm. It's good to be facile without you're not fumbling with it too much with your answers and stuff. But I think I got my signs right. Let's check and see. So I'm calculating the work that's done on the gas. You've all told me that it's going to be negative in this case. Let's check to see that that's true. V2 is bigger than V1. Log of a positive number